that's fine. I just have to be able to find the computer, but there's monitor lights, so that should be fine. That is the opposite. Okay, so my talk today is called Houston, We Have a Problem, the Perils exploration. So the first point I want to make is that launching things into space is hard. So there are some big considerations when you are designing space missions. What you bring with you is what you get, which means, and a second point is that you need fuel to maneuver. So once you run out of fuel, that's it. The more weight you add, the harder it is to launch, and the more fuel it takes to change your trajectory. And you also need to send things out very fast because space is big. And the faster you're moving, the more fuel it takes to change trajectory. And also, the farther out you go, the longer it takes to communicate back to Earth. So this is one of the reasons why New Horizons, which was the space mission that gave us all those awesome pictures of Pluto, was a flyby. It's literally because they had to basically hurl it out into the outer solar system very fast in order to get it there within a reasonable amount of time. So they couldn't physically carry enough fuel in order to slow down enough to orbit. So there are many ways things intended for space can fail. Sorry, microphone. Launch vehicle malfunction causing explosion. Probes stuck in orbit and unable to get to target. Malfunctioning instruments. Bugged software. Human error. Wacky coincidences. Once things are up in space, fixing potential problems becomes a lot more difficult, if not impossible. You can't exactly go out there with a wrench and fix things unless it's specifically been designed in the mission. And this has, from the beginning of space exploration, caused many problems. Here are some specific cases. So the first topic I want to talk about is probes and how space likes to eat them. So the problem with probes is, again, space is very big, plus communication signals travel at the speed of light. Well, the speed of light is very fast, but it also means it's also finite, which means that communication with probes is not instantaneous. For example, light from the sun takes a whole 8 minutes to reach Earth. And so if you're sending something far enough away, not only can you not physically go there to fix mechanical failures, but your signals will take several minutes to reach the spacecraft, so you can't react instantaneously to problems. This means landings, orbits, and course changes need to be automated. Ooh. If something goes wrong, ground control can't react in time to fix it. So the first of the probes I'm going to be talking about is actually a series of probes. And basically, the Soviets go to Venus. So sorry, there were some technical difficulties, so the fonts are a bit off. So between 1961 and 1984, the Soviets launched 28 Venus probes, some of them launching within days of each other. And so while some succeeded and gave us the first ground images of Venus, they also had about a 50% fail rate. So here is a screenshot of a table from Wikipedia that talks about all the Venus missions from 1961 to 1965. You can see all of the USSR ones and how many of them failed. But eventually they started succeeding and got some good data. So shenanigans included blowing up on the launch pad, failing to escape Earth orbit, loss of contact after launch, crashing into the planet, melting prematurely, instrument failure, lens cap failing to come off 4 times, lens cap coming off but landing on the spot selected for measuring soil compression. So my favorite quote about this is actually from the Wikipedia page on that particular mission, where they said they precisely measured the compressibility of the lens cap. So moving on from the Venus missions, now we're into Mars missions. So UNITS defeated the Mars Climate Orbiter. So NASA launched the Mars Climate Orbiter in December of 1998, and then NASA lost contact with it when the probe began orbital insertion. So the problem was that a piece of software used on the ground had actually been designed by a contractor, and that contractor used US customary units, inches, pounds, but NASA used metric. So The course correction burn was calculated in pound-force seconds versus the Newton seconds the NASA software was expecting. And so you can see here, the planned trajectory was further out, and then the actual trajectory was way too close. And the thing about atmospheres is you have to like come in at a very precise angle if you don't want to hit atmospheric friction and like bounce off the atmosphere. So what happened was the probe skipped too close to the planet, 57 kilometers above the surface, and skipped off the atmosphere, destroying it or sending it back into space. In other Mars missions, there was Mars Polar Lander, which was launched on January 3rd, 1999. It was intended to land near Mars's south pole. And shortly after it entered Mars's atmosphere on December 3rd, 1999, and well, this was originally an Avatar: The Last Airbender joke that was crossed out, but it did not translate over when we had the technical difficulties. So basically, it vanished, and they didn't hear from it when they were supposed to. So some speculation was that the spacecraft mistook vibrations from deployment of the legs as touchdown and cut the rockets early, but they don't really know. They're years and years later, they still have a list of possible things that happened, but they don't actually know. And the remains of the lander have not been found. And considering it's been 25 years since then, they're probably not going to be found ever, because Mars actually has weather, so things can get covered up. And this next probe was Beagle 2, and this was an ESA mission. So this was a British lander carried to Mars aboard the ESA's Mars Express mission. It was supposed to land on Christmas Day in 2003, but after it landed and it was supposed to contact ground, there was no signal. So what actually happened to it was a mystery until HiRISE, which was a Mars orbiter mission, actually managed to found it and photographed it. So basically the landing went off without a hitch, and then the probe started its operation. But what happened was that a couple of the solar panels were kind of folded on top of each other, and then when it landed, it was supposed to open those up. Something happened to prevent a couple of those panels from deploying, and the communication antenna was under one of the failed panels. So it wasn't able to get signal. And this one was one of my fellow graduate students back at U of M's favorite. So the ExoMars mission is a joint project between the ESA and now NASA. It was originally a joint program between NASA and Roscosmos, which has been terminated because of reasons. But the first of two missions launched on March 14, 2016, consisting of the Trace Gas Orbiter and the Schiaparelli EDM lander, which was pictured in artists' recreation. Schiaparelli was supposed to examine dust storms in the atmosphere. So they got there, the lander and orbiter separated 3 days before its arrival as planned so that it could continue on by itself. And then it entered Mars's atmosphere on October 2016. And then it crashed. So what happened? Well, the plan was to use its heat shield to slow down due to atmospheric friction, deploy a parachute to slow down even further, eject the heat shield so that it could uncover its landing gear and uncover the retro rockets so that it could slow right down as it reached the surface. So what actually happened, the lander begins its descent according to plan. The heat shield is released. The lander starts to spin really fast. It spins so fast that the instrument that measured rotation peaked for about a second. So if you want to think of peaking, if you take a picture with your camera and something is really, really blown out, it's reached basically the maximum ability of the sensor to handle it, and you're not getting any more data. So this convinced the navigation computer that the probe was underground. So it dumped the parachute, fired the rockets for a fraction of the time it was supposed to, and then considered the job done. It was still 4 kilometers above the surface. This next one I've called Philae Doesn't Stick the Landing. So on March 2nd, 2004, the ESA probe Rosetta was launched to rendezvous with a comet. 67P I'm sorry, I will not pronounce this properly. Chermunov Gerasimenko, 10 years. So on board was a small lander called Philae. And due to low gravity conditions, Philae's planned landing was complicated. The comet was not big enough to have a very strong gravitational field, so you can't exactly rely on that for you to come to a complete stop. So Philae's landing gear was to quickly screw it to the surface at the same time as rockets fired to push it down onto the surface, and then fire some harpoons to really stick it down. So Philae was released on November 12th, 2014. It touched down on the surface and then went on a merry journey bouncing around the comet for about 2 hours until it ended up in a crater over 1 kilometer away from the landing site, planned landing site. So what happened? Before Philae was released, the control team realized that the thrusters that were supposed to press it into the surface were malfunctioning. So they released Philae anyway. They didn't really have much choice. It took 10 years to get there. So the thrusters didn't fire. This was expected. What wasn't expected was that the harpoons also didn't fire. So Philae eventually came to rest in deep shadow on its side with not enough light to charge the batteries. And it managed more than 2 days of data collection before it went into hibernation. And the bouncing actually had the added benefit of allowing the team to compare the comet surface at both touchdown sites. So some discoveries that Philae made, it detected many organic molecules, which basically means carbon complexes, including 4 that hadn't been detected around comets before. And it provided some information on the comet's internal structure. And it did wake up a handful of times after the initial hibernation. So semi-success. So now we're going to move on back a little closer to home, talking about things that have gone wrong in and around Earth orbit. So the first of these is the Hubble Space Telescope and the case of contractor hubris. So some of you may not have known certain information about Hubble, which I'm going to get into here. So in 1974, discussions began on what was called the Large Space Telescope. So the reason why we want to put telescopes in space is that atmosphere doesn't interfere so much with our observations, and you can get much clearer pictures. That's just one of the reasons why. Sometimes you might also want to look at things, specific wavelengths of light that the atmosphere blocks out. So it was designed to be serviced in orbit. So this is one of the cases where you put it up in orbit and you can go and fix it. So they designed it so you could swap out the instruments as new discoveries happened and equipment got better. And it was intended to be serviced by the Space Shuttle program. So the original instruments, it had 5. So it had the Wide Field and Planetary Camera, Faint Object Camera, Faint Object Spectrograph, Fine Guidance Sensor, and the High-Speed Photometer. And the initial cost estimate when it was first conceived was $400 million US. Actual cost by launch was $4.7 billion. This was an expensive boy. The launch was originally scheduled for 1986, which did not happen for reasons I will get into later in this talk. So they had to put the completed parts into storage while engineers tweaked and updated various components. So Hubble launched aboard Space Shuttle Discovery on April 2nd, 1990, or April 24th, 1990, and was released into orbit on April 25th. And then they started collecting data. Oops. So what happened? So the way Hubble was constructed is also similar to the way some of the telescopes here are constructed. It uses light using a pair of curved mirrors, the primary and the secondary. So the primary is at the back and the secondary is at the front. And so Hubble's primary mirror has a diameter of 2.4 meters, which is about 1 1/3 times the size of the Plaskett telescope mirror up here. So mirrors and telescopes have to be ground very precisely, or they will introduce aberrations into the image. Oops. Also known as light will focus wrong. And so that's kind of what the light beam picture there. In a telescope, you want parallel light to come in and focus to a single point. And if you don't, you end up with something like that picture of a star, which was the actual picture of a star that Hubble took when it was first launched. So Perkin-Elmer Corporation won the contract to manufacture this primary mirror using a fancy new computer-controlled polishing technique. Remember, this was the 80s, and they flubbed it. So how did that happen? So Perkin-Elmer's technique used a specially built measurement device that used a laser to help guide the shaping of the mirror. Now, lasers can be used to measure things very precisely. That's why they're built into LIGO, which has made all those gravitational wave discoveries. They can measure very, very small changes in length. So, pop quiz. If your fancy measurement device doesn't fit together in quite the way you expected, do you A, figure out why, or B, make it fit? They chose B. So the wrong spacing meant the mirror was ground very precisely to the wrong specifications. So, fortunately, since Hubble was designed to be serviced in orbit, a fix was possible. If something like this had happened to James Webb, that would be it. We cannot get out there. It's way too far. But Hubble was in a fairly close Earth orbit, so it was designed to be serviced with shuttles. So option A was to replace the mirror. They did have a backup mirror that had been ground by Kodak using traditional methods, but the problem is, again, weight and complications. You'd have to have an astronaut disassemble the telescope and swap out the mirrors. This was considered too complicated. So option B was to work around it. So they opted to replace the wide field planetary camera with an upgraded camera with a built-in correction, which they called WPFC2, and to remove one of the existing instruments and replace it with glasses for the other three instruments. So this would basically correct the beam as it headed to the other instruments. So goodbye, high-speed photometer, and hello, corrective optic space telescope axial replacement, or COSTAR. Acronyms in astronomy are notoriously bad. So fun fact, these instruments had the same aberration as the mirror, but backwards. So it would allow the light to be focused. So, and then they started taking data, and much better. And this is why we've had so many good images from Hubble over the years. Can you imagine if that hadn't worked? Would have been bad. Okay, so this one is kind of relevant to my personal experience because at the time, Hitomi, which was like one of the probes the observatories I'm going to be talking about, was launched. I was taking the high energy astrophysics class at U of M, and certain of my cohort had theses that were hoping to use data from Hitomi. So what were Suzaku and Hitomi? So Astro-E, as it was originally called, was a joint Japan-US X-ray observatory, and it had 4 state-of-the-art instruments: the X-ray telescope, the X-ray spectrometer, the X-ray imaging spectrometer, and the hard X-ray spectrometer. So the reason why you want to put your X-ray observatories in orbit is because our atmosphere is very, very good at getting rid of those. So you actually literally need space-based telescopes for X-ray astronomy. So the X-ray spectrometer was particularly exciting because it was a new type of X-ray spectrometer that promised to have exceptional resolution. So if you think of spectra, it's like what you see when a beam of light passes through a prism. It spreads out into its component colors. And so what this would do was it would spread that out so much you could see very, very fine detail. So Astro-E launched aboard an MV rocket on February 10th, 2000. And then it blew up. So take 2, Suzaku. So they made another one. Astro-E2 launched on July 10th, 2005. It did not blow up, and it was given the official name of Suzaku. Then, just under a month later, all the liquid helium used for cooling that fancy spectrometer boiled off due to a bunch of cooling system malfunctions. So its spectrometer was now effectively useless, but the other instruments were unaffected. And the satellite continued operating until September 2015. So take 3 was Hitomi. So the reason they keep pushing for more of these X-ray observatories is currently there are 2 soft X-ray observatories in orbit right now, and they have been in operation since the 1990s. So one of those is the ESA's XMM Newton, and the other one is NASA's Chandra X-ray Observatory. And looks like NASA might be trying to, or the US government has been trying to reduce funding for Chandra, even though it's incredibly important. So because those 2 observatories are so old, if there isn't a new X-ray mission before ESA's new Athena observatory is supposed to go up in the late 2030s, there's going to be a huge gap in X-ray astronomy. So they're pushing more of these observatories. So they tried again. So they called this one Astro H originally, and it was designed to observe sources an order of magnitude fainter than Suzaku in both hard and soft X-rays. So Astro H was successfully launched on February 17th, and it was given the official name of Hitomi, meaning pupil. And everything seemed to be going well. It had started its calibration phase, and all the instruments were operating as designed. And then on March 26th, they lost contact. And it turned out Hitomi had spun itself apart. So what happened? It was an instrument malfunction. Is the video going to play? There we go. An internal mechanism registered a small rotation, about 22 degrees per hour, when there was no rotation actually happening. The spacecraft was idle. Click back on here. So the attitude control system responded by using the reaction wheels to counter the rotation. So it's basically started spinning something to put in a counter rotation for something that didn't exist. So the spacecraft began to rotate in the opposite direction. And the readings were still faulty, so it kept adding momentum to correct the rotation. And then it tripped the thrusters to attempt to stabilize, and it made things worse because Hitomi, much like James Webb, had been compacted to get it up into orbit, and then when it got there, it extended out that very long optical bench out there, and they hadn't quite updated the parameters for the spacecraft properly. So it made it worse. And then the spin was so extreme that it ripped off both solar panels and the extended optical bench. Rest in peace. And that video was basically someone on the ground pointed their telescope and they were able to see the remains of Hitomi spinning. Fortunately, XRISM, the follow-up to Hitomi, has successfully launched back in September and is finally putting that fancy spectrometer to the test. Here are some pictures from the JAXA website. And they should be commencing observations on proposed targets very soon. Although this one has not been completely free of technical difficulties because the spectrometer had a window in front of it to protect it during launch, and they have so far been unable to open it. The spectrometer does work though, but it just means that the lowest range of energies it's sensitive to are kind of cut off. So they're still working on trying to get it open, but it's operational, it's working. So this next one is something that's probably going to be happening a lot more as more of these giant satellite constellations are put into orbit. So satellite collisions have happened before, but most were like low-speed collisions. But on February 10th, 2009, we had one between a decommissioned propulsionless Russian military communication satellite. So this was unable to be controlled, no fuel, not able to move on its own, and it collided with an operational Iridium communication satellite at 42,000 kilometers per hour. So the resulting debris field produced around 1,000 large pieces of debris. Most of that debris has burned up in the atmosphere over the last 15 years, fortunately, and it happened at a high enough altitude that the ISS wasn't really in danger, though they did have to do a course correction several years later to avoid a cloud of debris. But this video shows a simulation. It's about a minute long. So this is how the Iridium satellites, communication satellites, orbited. And so we have Iridium 33 here, and the Russian Cosmos 2251. And they collapse. And because space, there's no atmospheric friction or local things for it to hit, they just keep moving. So their momentum has changed because they're now distributed in space, but they're just continuing their original orbits, slightly changed. Yeah. So something more to look forward to in the future. Which is why there's such a push to deorbit decommissioned things, but that causes its own problems. So yeah, this was, I believe at the time of the collision. I'm pretty sure it's much worse now. So now we get into the more serious topics, because these cases are where people actually lost their lives. And I'm going to be talking about why the decisions. So the first of these cases started near the beginning, which was the fire with Apollo 1. So the crew of Apollo 1 were astronauts Virgil Gus Grissom, Edward H. White II, and Roger B. Chaffee. And on January 27, 1967, the crew boarded the Apollo 1 command module for a routine test, because they were going to be launching in about a month. So the test was supposed to determine whether the spacecraft would operate on its own internal power. So the astronauts were sealed in. They upped the atmospheric oxygen and increased the pressure to simulate conditions in orbital operation. And then an electrical fire broke out, killed all 3 crew who were not able to escape the module in time. Now, oxygen-rich environments are incredibly flammable, so that's even worse. So the cause in this case is suspected to be linked to electrical arcing. Basically, the electrical system was not insulated well enough, and there were some discrepancies in the specifications. And then the increased oxygen in the cabin fed the fire, and since the hatches opened inwards, the crew couldn't get the hatch open because, again, they upped the internal pressure, and so it was forcing the door outwards rather than in. So the reason the hatch opened this way is that Gus Grissom had previously piloted a mission where the emergency explosive hatch accidentally blew after splashdown, and he nearly drowned. So they're like, yeah, we'll have it open inwards. That will avoid that. It took 5 minutes to open hatches from the outside, so they were not able to escape. And this pushed back the banned Apollo flights for 2 years. The next one is Soyuz 1, which was cosmonaut Vladimir Komarov. So Soyuz 1 launched on April 23rd, 1967, and the launch was rushed. Engineers apparently listed over 200 design faults with the Soyuz, but the launch was pushed forward anyway. Yuri Gagarin, the first man in space, was the backup pilot and tried to swap out Komarov, banking on the government not wanting to kill their hero. But Komarov refused for the same reason. So there were so many technical issues. A solar panel failed to deploy, instruments malfunctioned, and fatally the main parachute on the re-entry module failed to deploy, and then the backup tangled. So the retro rockets, which were again designed to slow things down as you get towards the surface, fired after the cap module had already impacted, and then it caused a fire that disintegrated it. There's no chance of survival. 11 Soyuz missions later, the crew of Soyuz 11 was the second crew to make a docking attempt with the USSR space station Salyut 1. So the crew were cosmonauts, hang on, let me start that, Georgy Dubrovsky, Vladislav Volkov, and Viktor Patsayev. And they were actually the first crew to successfully dock at Salyut 1, which I'm going to be talking about later in this talk. They successfully docked with the station on June 7th, 1971. And this was the first time that a space station had been manned, and it set the record for the longest time in space at 23 days. So the mission had been a success despite a fire, which had been non-fatal, and some minor issues, and included several live TV broadcasts. Then they departed on June 29th. The re-entry appeared normal, but when the capsule was discovered on the 30th, the crew was found dead. So what happened? This crew was originally the backup. The original crew had been replaced before launch when one was suspected to have tuberculosis, but it turned out to be an allergic reaction. The original mission commander didn't trust the automatic system based on his experience in the simulator and advised close the valves manually and before they left, and they didn't. They don't know whether this may have contributed to the problem because other things went wrong. So the pressure equalization valve was jolted open at module separation. Apparently, two small explosions that were designed to go off one after the other went off at the same time, which caused the valve to be jolted open, which exposed the crew to the vacuum of space, Later tests showed that manually closing the valve took almost a full minute, and the Soyuz crew would have been rendered incapable within 20 seconds. And these 3 remain the first and only deaths to actually occur in orbit. Now, this is closer to recent history, although it happened the year before I was born. The crew of the Challenger was Commander Dick Scobie, pilot Michael J. Smith, specialist Allison S. Onizuka, Judith A. Resnick, Ronald E. McNair, Gregory Jarvis, and Krista McAuliffe. The Space Shuttle Challenger was the second shuttle put into service and had flown 9 successful missions before the launch on January 28, 1986. Remember how I said the Hubble couldn't be launched in 1986? This is why. Before this, there were plans for many, many, many launches per year. They wanted to send up shuttles regularly. And this STS-51-L was the 24th shuttle mission. Its payload was a satellite and a small shuttle-pointed satellite that was intended to study Halley's Comet. However, this mission was also very special because it carried the first participant in the Teachers in Space program, Krista McAuliffe. NASA had committed itself to an unrealistic launch schedule since before the shuttles were actually in service. So the launch had been scheduled for January 22nd, but was delayed multiple times. So there were delays to the preceding mission that pushed it back. There's poor weather at the abort landing site. So the second where they were supposed to land if things went wrong during the launch. There were bad launch conditions at the launch site. And there were technical problems with the access hatch. And then there were bad crosswinds when they went to try to launch. And then the morning of January 28th, it was unusually cold, hovering around freezing. And despite the shuttle not being rated for those temperatures, they launched anyway. And then 73 seconds into launch, Challenger disintegrated, killing all 7 crew members. So what happened? So keep in mind, this was in Texas. There was this much ice on the controls around the. So what happened is that rubber O-ring seals on the booster rocket failed, which caused a breach, allowing burning gas to escape and damaging the fuel tank. The fuel tank ruptured, and then the boosters went their separate ways, and the shuttle was torn apart by aerodynamic forces. So the cause was a perfect storm of normalizing the abnormal, cold temperatures, miscommunication, confusion, and managers ignoring engineer warnings. So the first point I made is normalizing the abnormal. So the booster design of the rocket had a flaw. So under the extreme stress of launch, the booster housing had a tendency to balloon, so it would actually separate. So that's what that first picture is showing. It's like a cross-section of the wall of the booster. And so this would happen. It would allow hot gas to escape. But the O-rings, which are the little circles in the cross-section there, would actually, one of them would dislodge and it would fill in the gap. Problem solved. This happened multiple times. But since it seemed to be a self-correcting issue, they left it alone and just increased the damage tolerances, acceptable damage tolerances, which didn't mean that damage was okay. They just said, yeah, fine. But the colder rubber gets, the more stiff it becomes, the longer it takes to fill the gap, the more damage it takes, and then you have what happened to Challenger. NASA engineers had actually sounded the alarm about the joint issue before the design was approved in 1980. This was not forwarded to the contractor. Managers also downplayed previous O-ring issues in their reports. So the managers were so determined for Challenger to launch that the engineers had to justify their reasons not to launch instead of the other way around. They really wanted to launch. The booster contractor threw together a hasty presentation to try and back up their assertions, but they failed to convince the managers and their concerns weren't passed up the line. I believe the first 2 slides up top were from the engineer presentation. The one on the bottom was something that was put together after the disaster, and it shows the number of O-ring incidents with plotted against temperature. And you see that the flights with no incidents all happened 65 degrees Fahrenheit. And they failed to convince the managers their concerns weren't passed up the line. So the aftermath. Space shuttle flights were halted for almost 3 years, and they resumed in September 29, 1988. In that time, the booster rockets were redesigned and the new model came back pristine after 110 launches. So NASA scrapped the plans for non-astronaut passengers, and the Teachers in Space program closed in 1990. Though it was replaced by the Educator Astronaut program, the teachers in the program are fully trained astronauts. So in 2017 and to 2018, astronauts Joe Acaba and Ricky Arnold carried out Krista McAuliffe's lesson plan. And that's how things progressed from there. Now, the space shuttles went fine until Columbia. I remember this one because that was the day I was having a driving lesson and the instructor turned on the radio to listen to what they were talking about. So the crew of Columbia was Commander Rick D. Husband, pilot William McCool, payload commander Michael P. Anderson, specialists Kalpana Chawla, David M. Brown, Laurel Clark, and Ilan Ramon. On January 16th, 2003, Columbia lifted off from the Kennedy Space Center. The mission lasted 25 days, performing a variety of successful experiments in orbit before initiating return on February 1st, and then Columbia descended minutes before it was due to land. So, what happened? A piece of foam insulation was dislodged during launch and damaged the heat insulation tiles on the left wing. When the shuttle began its descent, hot gas ripped into the wing. So that's it pictured in the zoomed in picture there. You'd think that foam wouldn't cause a lot of damage, but when it's moving very, very fast, it can hit very, very hard. Foam strikes had superficially damaged the shuttles, and it happened 4 times already, but sometimes it caused significant damage. Like with the O-rings, it had been something that had become normalized, and this time it just happened to impact in a spot where it caused the most damage. So based on previous results, NASA okayed the return despite not knowing the extent of the damage and denying engineers' requests for imaging. So the aftermath of Columbia was shuttle missions were again halted for over 2 years. The investigative board concluded that if NASA had moved early enough, they could have gotten a second shuttle up to rescue the crew, but Columbia would have had to have been scrapped. NASA later added remote piloting to shuttles so they could return unmanned. Repairs would have been possible, but had a high chance of failure, and would have had to be kludged together from cabin materials. All future shuttle missions, except the last Hubble repair in 2009, were flown to the International Space Station. A second shuttle was kept prepared in case rescue was necessary, and all missions were required to thoroughly inspect for damage after launch. So now we get to calm back down. Here are some things that people survived, so they are less fraught. So the first one is that the Vostok 1 modules want to stay together. So the first manned space flight launched on April 12, 1961, carrying cosmonaut Yuri Gagarin. The flight lasted 108 minutes, and he completed one orbit of the Earth. And the re-entry module was supposed to separate from the service module before it re-entered, but it remained connected by a bundle of wires. The re-entry forces eventually separated the modules, but produced a ridiculously bumping ride. So it subjected him to about 8 Gs of force. So I'm standing here, there is 1 G of force acting on me, multiply that by 8 times. He opted to eject from the module and landed successfully. So this next one is about the first spacewalk by Alexei Leonov. So Voskhod 2 launched March 1965, carrying cosmonauts Pavel Belyaev and Alexei Leonov. So on March 18th, Leonov became the first human to perform an EVA, floating outside the module for 10 minutes. And apparently this goal had been kept secret prior to launch, so his family were watching and was like, why is he outside? What's going on? But everything was fine, but then he went to go back inside and he realized there was a problem. His spacesuit had inflated like a balloon, which made the re-entry into the module impossible. Remember when I was talking about pressure? So the suit is pressurized internally, there's lower pressure in space, so that caused it to expand. So he had 40 minutes before his life support ran out, so he decided the only way in was to go in head first. So in order for this to be successful, he had to vent his suit to reduce pressure, and then he had to kind of force his body to curl up so that they could close the hatch. The effort he had to expend heated up the suit, but he got in safely, and then they prepared to come back to Earth. And then the malfunctions happened. Uh-oh. So instrument checks showed the automatic landing system wasn't working properly. They'd have to descend manually, and they only had enough fuel for one attempt. And then the landing module failed to separate from the orbiter, causing it to spin with more than 10 Gs of force to the cosmonauts before disconnecting. And then they landed 400 kilometers from where they were supposed to, but were deep in taiga forest, freezing weather with no heater. A civilian search party managed to find them fairly soon, but they weren't equipped to rescue them, and they were officially rescued a couple days later. But they made it. Now, the first docking attempt with Salyut Mun also makes it useless, almost makes it useless. So on April 19th, 1971, the USSR launched Salyut 1, which was the world's first space station. This was quickly followed up 3 days later with the launch of Soyuz 10, a manned module intended to dock and transfer crew to the station. The crew was able to navigate to the space station without issue, but there was a problem. During soft dock, so before all the seals were closed, the module's computer decided it wasn't aligned properly, and it fired thrusters to compensate. And then this prevented hard dock, so the mission had to be aborted. So here's a big catch-22. When they went to undock, they realized that part of the interface was stuck. It needed an undock command from the station. As far as the station was concerned, they weren't docked. So the options: cut loose the docking system, or disconnect from the Soyuz orbital module. Both of these would mean that the station would need to be abandoned because there would be no way to transfer crew on board. Fortunately, they were able to hotwire it to get it free. They had to flip a breaker. So now here's a more famous one. So very many things go wrong with Apollo 13. So Apollo 13 was set to be the third manned mission to the moon when it launched on April 11th, 1970. Despite a launch engine malfunction, Apollo 13 managed to get into its planned parking orbit and then continued on its path to the moon, which would take 3 days. And then just over 2 days into the mission, an oxygen tank exploded, taking out a second one and then cutting off water production and power to the command module. So, but it didn't damage the lunar module. And I think that like the neat thing about the Apollo lander module situation is that it basically stuck the lander upside down to its nose and then like pushed it through space. So basically they were able to actually camp in the lunar module. So the lunar module allowed them to power down the command module systems to conserve power, but course corrections had to be made to send the module back to Earth manually. So because there was so much debris from the explosion, they couldn't really lock onto any stars, and so they had to use the sun to get the correct angle. And then they had to perform a short burn to get them into a figure-8 orbit around the moon. It's what's called a gravity assist. So this would allow them to turn around without having to burn thrusters. So fortunately, about 4 days after the explosion, the cold, dehydrated, emaciated crew touched down safely in the Atlantic Ocean. And last time I gave this talk 5 or so years ago, I rented Apollo 13 and watched it. It's a good movie. This next one was, if you can tell, for each section I'm going in chronological order. So this one was when a resupply module crashed into Mir. So Mir was put into service before the fall of the USSR and was resupplied by unmanned missions. The original docking system was manufactured by a company in Kiev, but after the USSR dissolved, they began charging through the nose. And so they decided to test a different system and failed to adequately train the crew. So on June 25th, 1997, they attempted to test the new system on Progress M34 without ground radio contact. Progress approached at high speed behind the solar panels and prevented the crew from seeing it. And then the predictable happened. Progress crashed into the solar panels and ricocheted into the Spectre module, causing decompression. Crew members managed to quickly seal off the module, saving the station, but severing the power from the solar panels. Spectre stayed depressurized, but they were eventually able to route power and remote control the solar panels several months later. So it didn't destroy the space station, but close call. And then this one happened around the last time I gave this talk, in that somebody drilled a hole in Soyuz MS-09. So at night on August 29th, 2018, a slow leak was detected in the International Space Station and found to be coming from the docked Soyuz MS. Inspection found a 2-millimeter hole in the hull. At first, it was assumed to be from a meteor strike, but then closer inspection revealed that it had been drilled from the inside and hidden with a low-quality patch job. The patch with epoxy, since it was not going to re-enter. So possibly happened during the manufacture. And then I was looking into follow-up information because, like I said, the last time I gave this talk was about 5 or so years ago. And apparently the officials in the Russian government tried to claim it was the American female astronaut who did it because she wanted to go home early for no reason. Well, I mean, she had a medical issue, but the fact that they decided to blame this woman for no reason is unfathomable to me, even though it's the most likely happened during manufacture. So in recent news, there are currently 2 astronauts strapped in orbit. So on June 5th, 2024, Boeing launched the first crewed flight of the Starliner, carrying astronauts Sunita Williams and Butch Wilmore to the ISS. The Starliner was plagued with issues since before its launch and managed to spring several helium leaks and propulsion system issues on its way to the ISS. The original stay on the ISS was supposed to be 8 days long. Testing on the ground and in orbit has left NASA leery of trusting the Starliner returning Williams and Wilmore safely, so it's looking more and more likely that they're going to either be stuck there until 2025 or they may have to go to SpaceX for a rescue mission. Boeing is of the opinion that, oh yeah, it'll be fine. NASA's doing the right thing here. So final lessons from this overview. Space is hard. Haste makes waste. Test everything several times in multiple ways. Operational limits exist for a reason. Communicate. Redundancy, 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 redundancy. Listen to the engineers. And that's the end of my talk.